Hello everyone, this is Dr. Webb, and welcome to the first video for Math 430 Abstract Algebra 1. So in this video, we're going to be covering some review topics that are in Chapter 0 of Galleon's text, Contemporary Abstract Algebra. And so probably most, if not all, of the topics in this video are review. Probably from what you saw in discrete math, or possibly you covered this if you took a number theory course. So let's jump right in. Okay, so topics we're going to go over in this video, we're going to talk a little bit about divisors and the division algorithm and modular arithmetic. So in all of this, we're going to be talking about things dealing with the integers, and so the integers are going to pop up an awful lot in this course. So let's get on the same page with that. And then also we're going to talk a little bit about equivalence relations, because those pop up quite a bit in abstract algebra. So in most of this, I'm not going to go through full proofs. I'm hoping that you've seen the proofs already in your discrete course. But also the proofs for this are not, the facts are more important than the proofs for most of these. So the statement of the theorems are useful. How they are proven, that would be a little bit too much of a tangent. It's not so important for what we're going to need in the course. Okay, so let's start off with what divides mean. So again, as we said, we're going to be talking pretty much exclusively about integers in this video. So if we say that n divides m, which we write n/m, then that means that there is some integer that we can multiply to n to get m. And so, for example, we'd say that, say, 3 divides 12, and we know that's true because I can multiply 3 by 4 and get 12. So 4 is playing the role of k, where 3 is n and 12 is m in this example. And so this is a notion that should be very familiar with you if, say you ever went to elementary school. So what are some basic properties of being a divisor or dividing something? Well, first of all integers divide themselves. And that's just because I can always take n and write it as n times 1. 1's an integer, so 1 times something, that gives me back what I started off with, and so that says that n divides itself. In the same way, this also is telling us that 1 divides every integer, because you can always take 1 and then multiply it by that integer and get the integer back. So one that people often forget, but is important: every integer divides 0. 0 does not divide any integer except for itself, but every integer divides 0, and that's just because if you take any integer and multiply it by 0, 0 is a perfectly good integer. What do you end up with? 0. And so that tells us that n has to divide 0. Lastly, if L divides K and K divides M, then that means that L is going to divide M as well. And so this property here, this is often called transitivity. And, quick reason for this: if L divides K, that means L times R is equal to K. If K divides M, that means there's some S, such that when I do K times S, I get M. And so then just substituting in, you get L times R, which is K, then multiply it by S, gives me M. So L times RS gives me M, and so RS is an integer, and that tells me that L divides M. Okay, given two integers, often we're going to talk about the greatest divisor of the two of them, and we'll denote that as the GCD of s and t. And so it is the largest integer that divides both s and t. Right, so if we wanted to do GCD of, say, 12 and 18, that's going to be 6. Right? Because if you take the divisors of 12, that's going to be 1, 2, 3, 4, 6, and 12. Divisors of 18 are 1, 2, 3, 6, 9, and 18. What's the largest one they have in common? Well, they both have 6 in here. And so that's why 6 is the greatest common divisor between the two. Yeah, so for example, 12 and 18 is 6. Okay, so now let's move on to the division algorithm. So given two integers, and we want our b to be positive, then there are unique integers q and r, with r being strictly non-negative and smaller than b, such that a is equal to b times q plus r. So this is just sort of a very formal way of writing out, what you learned when you did division, say, in fourth grade. As an example, let's let a be 45, b be equal to 7. Well, we can write 45 is equal to 7 times 6. That gives me 42. And then I need to add 3 more. And so in this case, our q is equal to 6. Our r is equal to 3. And note that 3 is between 0 and 7. And so if you want to think back about, how you were taught how to do this in elementary school, this is equivalent to, well, what happens when you do 7 divided by 45. Well, you'd multiply it by 6, end up with 42. 45 minus 42 is 3, and so you'd say that 7 divided by 45 is 6, remainder 3. And so the r is there for remainder, and the q there is for the quotient. So now let's move on to talking about modular arithmetic. So we have integers a, b, and n, and we need n to be at least equal to 2. So we need n to be positive, and doing modulo 1 is not done because everything would be congruent to 0 mod 1. And so 2 is going to be the smallest thing that we ever use as a modulus. In fact, this is a bit of a tangent, but if you ever see something talking about modulo 1, then actually it's usually talking about decimals. So that's modulo 1 is reserved for talking about decimals. If you ever are talking modulo any integer bigger than 1, then you are absolutely not using decimals in pretty much any way. So our n's are always going to be greater than or equal to 2. Then we're going to say that a is congruent to b modulo n if n divides the difference between these two numbers. So for example, we would say 3 is congruent to 15 mod 12, and that's because 15 minus 3 is 12, and so 12 divides itself, so 12 divides 15 minus 3. Okay, so I know that this is the first time seeing it, this might seem like kind of a strange notion, but it's actually something that you're actually pretty familiar with, and that you've actually been using it for a while, and just haven't called it this technical name. And so, this is done how we treat time. Really, when we think about time, we're usually working in modulo 12. If you're in the military, then it would be modulo 24, but it's the same idea. And so the idea is we can kind of illustrate in this example, if at 10 o'clock you start binge watching a show on Netflix or Hulu or whatever, and you watch for 5 hours straight, what time is it going to be when you're done? Right? Well, we all know the answer is going to be 3 o'clock. So how did we come up with that? Well, so if we start off with 10, add 5, we get 15, right? But when we usually think about time, we're dealing with things in sort of implements of 12. 15 is bigger than 12, so then what do? Well, we're going to subtract that 12 off and end up with 3. And so then we're going to say we're going to be done at 3 o'clock. Well, how does this relate to modular arithmetic? Well, as we saw before, 15 is congruent to 3 mod 12, right? And so if we wanted to talk about, if we were watching starting at 10 o'clock and then watching for, say, 2 days straight, 48, what time would it be? Well, 10 plus 48, but again, we're still looking at this modulo 12. Well, 48 is a multiple of 12, so I haven't really changed anything, and so it's still going to be 10 o'clock, right? So 48 hours after whatever time it is going to be the exact same time again. So fun fact, and this is often, when you're learning about modular arithmetic, this is something that people often use a lot to think about it. But if you have integers b, n, and r here is strictly less than n, is non-negative and less than n, then b is going to be congruent to r mod n if and only if r is what you get when you divide b by n, right? So r is the remainder. And so when people think about this being congruent to modulo, they often think about it as dividing by n and finding the remainder. That is how you find the smallest positive or smallest non-negative number that's congruent to something mod n, is dividing by n and finding its remainder. So one of the things that's interesting, in fact very useful about modular arithmetic, about this congruence modulo n, is that we can do basic arithmetic, adding, subtracting, and multiplication with it the same as we would do with an equal sign. If we have a is congruent to b mod n and s is congruent to r mod n, that was a little typo, but I think I fixed it pretty well, then you can interchangeably swap between a and b and s and r, and it doesn't change any of what you get when you're working mod n, right? So you can do a plus r, that's going to be the same thing as doing b plus s mod n. A minus r is going to be congruent to b minus s mod n. And a times r is going to be congruent to b times s mod n. So we can say, as we've seen, we have 3 is congruent to 15 mod n, mod 12. We can use that 7 is congruent to, let's use negative numbers, because this works for integers, and so you can use negative numbers as well. So 7 is congruent to minus 5 mod 12. And so if we do 3 minus 7, that would be minus 4. And I can add 12 to that and get 8 mod 12. And if I do 15 minus 5, so that's 15 plus 5, gives me 20. That's also congruent to 8. mod 12. So swapping 3 for 15 and 7 for minus 5, that doesn't change anything when we do the subtraction. Similarly, if we do 3 times 7, so that's 21, subtract 12 off from that, so it's congruent to 9 mod 12. If we do 5 times minus 15 times minus 5, times minus 5, well, so that's going to be minus 75. And so minus 75, if I add 84 to that, so this is going to be congruent to minus 75 plus 84, because 84 is a multiple of 12. And so what do I get? 9 mod 12. Okay, so swapping 3 and 7 with 5 and minus 15 hasn't changed anything. Okay, so this congruence modulo n, this is an example of what's called an equivalence relation. So what is an equivalence relation? Well, it has 3 properties. One is that it's reflexive, and so every integer is congruent to itself, mod n, right? Because a minus a is 0 and n divides 0. Every integer, if a is congruent to b mod n, then you can swap the place of them. B is congruent to a mod n, and that's just, if n divides b minus a, so that only happens if you have n times k is equal to b minus a for some integer k. Well, then you could swap you'd swap k with minus k, and that's going to give you a minus b. And so that's telling you that b is congruent to a mod n as well. So like an equal sign, it doesn't matter what's on the left, which one's on the left and which one's on the right. What matters is that they're congruent to each other. And the third property is this transitivity, same as we saw with division before. So if a is congruent to b mod n and b is congruent to c mod n, then that means that a is also going to be congruent to c mod n, right? And so if we think about all the numbers that are congruent to 3, so it'd be 3, 15, and 12 to that, 27, 39, etc. So we could subtract off 12s as well, so minus 9 would be the next one, etc. So these are all the numbers that are congruent to 3 mod 12. And so this is saying that 3 is congruent to 15 mod 12. 3 is congruent to 27 mod 12. Well, that also means that 15 is congruent to 27 mod 12. That's what the transitivity is giving us. Right, so if we think back about divides, which we talked about earlier, that is also a relation, but it is not an equivalence relation. So why is divides not an equivalence relation? Well, it is reflexive, because every number divides itself. And it is transitive, because we saw that it was transitive when we were talking about divides. But it's not necessarily symmetric. Right? 3 divides 12, but 12 does not divide 3. And so because it fails symmetry, then it can't be an equivalence relation. Okay, so once we have an equivalence relation on a set, we can start talking about what are called equivalence classes. So this, hopefully you covered this in when you took discrete math, but if not, we can talk about it now. Okay, and so when we have a equivalence relation on a set S, and you take some element, so in this case x, then the equivalence class of S containing x, or sometimes we'll just say the equivalence class for x, is the set of all elements of S that are equivalent to it. So it's all the y such that x is equivalent to y. So for modulo, this tilde here, this squiggle here, is this congruent mod 12, or mod n, whatever. Okay. So for example, when we saw this written out in the last slide, what's the equivalence class of 3 modulo 12? Well, it's all the integers that are congruent to 3 mod 12. So minus 21, minus 9, 3, 15, 27, 39, etc., etc., etc. Okay. So if you're given two elements in our set and you have this equivalence relation, then between these two elements, exactly one of these two cases must be true. So either they are equivalent to each other, and because of the properties of an equivalence relation, then if they're equivalent to each other, if you look at their equivalence classes, they are going to be exactly the same. And that's really coming from transitivity. If A is congruent to C, then C would be in the congruence class of A. But then by transitivity, B would also be congruent to C. So C would be in the congruence class of B, and vice versa. So that tells us that the two are equal. On the other hand, if they're not equivalent to each other, then their equivalence classes can't share anything. They have to have their intersection has to be empty, in which case we'd say their equivalence classes are disjoint, right? If A and B share anything in their equivalence class, then by transitivity, they'd have to be equivalent to each other. So if they're not equivalent, that means that they can't share anything in their equivalence class. Well, so this gives a natural, what's called partition of the set. So what does that mean? It means that we can break the set up into separate pieces that don't intersect each other at all based on the equivalence relation. So let's think about this. We've been doing a lot with modulo 12, so let's keep going that way. So for an integer a, we're going to let a bar denote the equivalence class of a. So this is all the numbers that are congruent to a modulo 12. Okay, well, you can think it out. So based on what we saw before with remainders, well, what are all the possible remainders you can get modulo 12? Well, that would be 0 through 11. And so if you take any number and divide it by 12, you're going to get one of these remainders. And so when we take the equivalence class of each of these remainders, every integer is going to fall into one of those. Okay, so this gives a partition of all of the integers modulo 12, because every integer is going to fall into exactly one of these classes. And so this kind of gives us a new set, which we're going to call the set of integers modulo 12. So the notation of that is z slash 12z, and which is just going to be this set of equivalence classes. And so we're going to call this the set of integers modulo 12. And then what we saw before is that you actually can do the arithmetic on these equivalence classes, because this modulo arithmetic plays well with each other. And so I can talk about if I take something in the equivalence class of 2 plus something in the equivalence class of 3, I'm going to end up with something in the equivalence class of 5. If I take something in the equivalence class of 7 times something in the equivalence class of, say, 10, so I'm going to get 70, which is also in the equivalence class of 10 modulo 12. Right? So we could say 7 times 10 is equal to 10. Because if I take anything in the equivalence class of 7 times anything in the equivalence class of 10, I'm going to end up with something that's congruent to 70 modulo 12. And so 70 modulo 12 is congruent to 10 modulo 12. Okay. So that's all I have for you for this video. I will see you soon.